we learned that if it is a strain gauge, it is basically resistance changes with the applied strain. And the change in resistance versus applied strain is given by, expressed as del R by L, del R by R divided by del L by L, that is the length of the strain gauge like this. And this is actually constant for a material which is given by 2 into mu plus of del R by R divided by del rho by rho divided by del L by L. So del rho is the resistivity and L is the, as mu is the Poisson's ratio. So these two things we have seen, and this change in resistivity per strain, this is due to what we call it piezo resistance effect. This is known as the piezo resistance effect. We have also seen that the strain gauge are mainly foil type strain gauge, and there are two types of this one. One is a metal strain gauge, mostly they are some alloys like advanced nichrome, different alloys like this, and their gauge factor normally varies between 2.0 to say 3.5 or 4 or like this. And we have a semiconductor type strain gauge where gauge factor can vary between up to plus minus 100, and plus and minus depends upon whether the semiconductor type strain gauge is P type or N type. So semiconductor strain gauge is definitely very sensitive, but at the same time it is a non-linear also. And we have seen the construction, that is a metal foil type, how to bond it and etc. We have just told it, but you may go through any book because these are very standard thing. You may go through any book and study this one. So now our thing that we had considered that and we had also what we called it Rossets. Where several strain gauges are placed one after another, one by after another, to measure strain in different direction and different axes. So these are called strain gauge rosettes. We have also discussed this one. Now what we have, we go for the signal conditioning circuit. And we have also, before that, we have also seen that strain gauges are available in standard 120 ohm, 350 ohm, 1000 ohm, like this. These are available, standard available strain gauges are there. And we will have to also pass some current such that it does not cause the self-heating. So current has to be limited by this one. So Now the signal conditioning circuit. And we have seen that if it is a gauge factor of 2 and like this there, and normal strain is experienced, it is maximum 10 to the power minus 3 strain. So basically delta R by R is equal to G into epsilon. So it is approximately say 0.2% or 0.3% change in resistance. So it is very small, so but we need to have to amplify the other things there and also amplify the voltage here, but the nonlinearity problem is not there. So the best thing is that the signal conditioning one is what we can say is a use a bridge. So what we have, the basic thing is that, say suppose this is your strain gauge and these are fixed resistances R, and I measured the voltage E0 across this one and capital E is this one. So it is quite simple, but the major issue for this one is that we are using 3 fixed resistance and 1 single strain gauge. The major issue is that temperature compensation. So this temperature compensation means this strain gauge, these are metallic or semiconductor, their resistance is very much temperature dependent. So if their resistance is temperature dependent, with temperature also the resistance will change. So as a result, we will not be able to distinguish that whether the change in resistance is due to strain or due to the temperature. So naturally, this is a major hindrance for the measurement of this one. So what we do is that there are two options there. Option one is we use a dummy gauge. Dummy gauge means uh, a strain gauge, another strain gauge which is mounted on the same structure where you are measuring the strain, but it is not, strains, but it is not subjected to strain. Maybe an identical structure, you place the the dummy gauge over it, but you don't apply any force or any strain. So what will happen? The advantage of this dummy gauge is that, but these two are the fixed resistance there. So one is the strain gauge, which is, we call it an active gauge, which changes the resistance, and one is the dummy gauge, which does not change the resistance. Resistance does not change due to the strain there, because no strain is applied. So what will happen in this case? What we have is that we can have a perfect temperature compensation, since the both the if the temperature rises, both the two and they are the identical strain gauge, so both the resistance will change to the same extent. As a result, the bridge remains balanced. So as a result, the bridge remains balanced and it does not vary. It is insensitive to the temperature. So what is the thing is that definitely the dummy gauge has to be placed in one of the adjacent arms. So it has to be in adjacent arm, but not in the opposite arm. Because in the opposite arm, you can easily see that you will not be able to compensate. So what we can say, it's an one way option one is there. Another option is that is use two active gauges. So what I am doing is that instead of, because the dummy gauge is that it is not experiencing any strain, and that will cause you more problem, or like this, to make it like this. So better you connect two strain gauges. This is also active strain gauge, and this is also another active strain gauge. So here it is, I call it 1, 2, 3, 4. If it is like this, both of them are active strain gauges, 1 and 2, but what is that? They are made in, they are being connected in such a way that if this strain gauge resistance increases, this strain gauge resistance will decrease. So maybe this R into 1 plus P, and here it is R into 1 minus P. So we'll come to this one, how it is achieved. But what we are doing is that if one is experiencing is a positive strain, the other one, active gauge, is experiencing a negative strain like this, identical for the time being, I am assuming. So the point is that when no strain is applied, but the temperature increases, both of them, the resistance will increase by the same amount, but the bridge will remain balanced there. How can you achieve that? How this positive and this active, two active strain gauges, how can you connect them? We can connect them by, say, we just consider a cantilever. Say, like this, at the end I apply some force. Now, if I put a strain gauge on the top of it, which measured the strain in this direction, and on the bottom of this surface, I put another strain gauge at the bottom of it. So the point is that if this strain gauge measures a strain of plus epsilon, this rather experience a strain of plus epsilon, the other, which is at the bottom, will experience at a resistor, a strain of minus epsilon. As a result, the complete temperature compensation will be achieved, but at the same time, the sensitivity will be doubled. So, double sensitivity. Obviously, we can also do another thing. Instead of connecting at the bottom, I can put it on the top itself, but in a perpendicular direction to the first strain gauge. So what will happen in this case, if it is plus mu epsilon, the second one will experience minus mu into epsilon. So as a result, one will be, maybe this will not be the same P, but one will be experiencing positive strain, another will be experiencing negative strain. But what is our intention is also that what is our intention is also fulfilled, because it will, both of them, both this configuration will be temperature compensated, and obviously that is there, and the sensitivity will also be doubled there. And of course we can have a, so it is a two-arm bridge, or rather two strain gauge bridge we will have it. But we may have a we may have the four-arm bridge, four-strain active strain gauge bridge. So it is two active strain gauge bridge, I must say, active strain gauge bridge. But there could be four active strain gauge also. That means I connect these two, the 3 and 4, as well as the uh, active and identical strain gauge. And only thing we'll have to see that they are connections in such a way that they are the positive strains are in the opposite arms and the negative strains are also in opposite arms, and positive and negative should be in adjacent arms there. So that is what we have it, and so naturally we can have also a four active bridge strain gauge bridge. And this is the thing which we have familiar with, we have seen, which we had called a load cell, that is a cylinder over which I apply an force, and two strain gauges I connect them to vertically, and two strain gauges I connect them to horizontally, and I make it 1, 2, 3, 4 like this. So we can have a four active strain gauges also there, and then four active strain gauges are also there, but they would be perfect temperature. Now we will go into a little bit because more detail, because the question may come that okay, suppose there are four strain gauges. In a more general case, there are four strain gauges, all are active, but the strain gauges may be different, they are maybe experiencing different strains and etc. How would you calculate the unbalanced voltage? Of course, we can do it by solving Wheatstone bridge, the same thing, but there is a way by which we can develop an approximate formula by solving, by using this one, we can directly get what is the unbalanced voltage there. So for that one, I would be doing slightly modifying this one. So I just consider four strain gauges, all are active, and I take the most general case like this and say suppose this is R1, this is R2, the third one is R3, and the fourth one is R4. So four active strain gauges are there, they are connected, maybe different resistance etc. there. The resistances may be R1, R2, R3, R4, and they may be all experiencing different strain. So what would be the unbalanced voltage and how to calculate that unbalanced voltage? So that and get a formula, develop a formula so that we can easily remember and just we can do that. So for that one, I slightly change it for the sake of simplicity. Say suppose the battery polarity I have changed compared to the last time. It is E, R1 and R3 are two strain gauges where the resistance is increasing. R2 and R4 are two other strain gauges where the resistance is decreasing. So from that one we can say it is E0 is equal to capital E into R1 divided by R1 plus R2 minus R4 divided by R4 plus R3. Okay. And we know at balance R1 by R2 is equal to R4 by R3, and I say it is A, is the bridge arm ratio. So you can see that in this case, so at balance E0 is equal to not E0 is equal to 0, the bridge is balanced. Now suppose this R1 changes, everything changes by a small resistance, R1 plus delta R1. I put it in a more general one, it is R2 plus delta R2, R3 goes to R3 plus delta R3, and R4 goes to R4 plus of delta R4. So in that case, we can easily write down, obviously, that it is E0 is equal to E into R1 plus delta R1 divided by R1 plus delta R1 plus R2 plus delta R2 minus of R4 plus delta R4 divided by R4 plus delta R4 plus R3 plus of delta R3. Okay, I can write it down. So, sorry, why? This is the thing there. Okay. So, if I so we can neglect delta R1, delta R2, etc. in the denominator. Because you see, this delta R1, these are all adding up. So that if they add up and there is nothing there, so delta R1, delta R2, delta R3 are all small. So we can say that they are all same there. Okay. So you can write it down is that, just a minute. We can write down as is equal to, if it is E into, I make it R1 plus delta R1 into R4 plus of delta R4 plus of R3 plus delta R3 minus of similarly R4 plus delta R4 into R1 plus delta R1 plus of R2 plus delta R2 divided by, I just make it simpler, so it is R1 plus R2 into R3 plus R4. Okay. So if it is so, I can expand it, because in the I cannot neglect all delta R1, delta R3 or like this in this way, because there is a negative term here. So it cannot do, so numerator I cannot approximate it in that manner. But what we can do is that neglecting the two multiplications of two increments, delta R1, say suppose delta R3 into delta R3, delta R4, delta R4 into delta R1. So, etc. So, what we can say is equal to E0 is equal to what I can say that it is E into R1, R4, then it is R1 plus of R1 into delta R4 plus R4 into delta R1, then what it remains? R3 into R1 R3 into R1 and similarly R3 into delta R1 . This way I can just go over like this and minus of other terms also and divided by R1 plus of R2 into R3 plus R4. So I am just simply expanding this one and I can get it like this. If we simplify it and neglect this part, this comes to be, so definitely we are neglecting, so it must be approximately equal to this one. And we will find this R1, R4 and R1, R4 gets cancelled out. Similarly, R2, R4 is equal to R1, R3. So they also get cancelled out. So we can simplify it and write it is equal to E into R1 delta R3 plus of R3 delta R1 minus of R2 delta R4 minus of R4 delta R2 and divided by R1 plus R2 into R3 plus R4. So now you can go a little bit simplify and come to the expression which is easy to handle. So we know that R1 I R2 is equal to R4 by R3 is equal to A. So our E0, mind it, these are all approximate. So like this I can say it is, if I take out E divided by, I can take out R2 and I can take out R3. So what remains? 1 plus R1 by R2, which is A, and 1 plus R4 by R3, which is again A. So it is 1 plus A whole square. And into, obviously, R1 delta R3 plus of R3 delta R1 minus of R2 delta R4 minus of R4 delta R2. So with this one, if I take out the R2 by R3 inside this one, I can write it down as E is equal to 1 plus A whole square. And here what is this? R1 by R2 into delta R3 by R3 plus of, I can write, so it is delta R1 by R2. I can write it down as R1 by R2 into delta R1 by R1 minus of, what is it? Delta R4 by R3. So I write it R4 by R3 into delta R4 by R4 minus of R4, sorry, R4 by R3 into delta R2 by R2. So I get a very nice expression, and since we know R1 by R2 is equal to R4 by R3 is equal to all A, I can write it down is equal to E into A divided by 1 plus A whole square. And what is it? You see, very nice expression. I need not derive this one always, but I can make it like this. R1 by delta R1 minus R2 by delta R2 plus of delta R3 by R3 minus of delta R4 by R4. So finally it's a nice expression. It is, what is delta R1 by R1? It is G1 into epsilon. So here it is EA divided by 1 plus A whole square into G1 epsilon 1 minus G2 epsilon 2 plus of G3 epsilon 3 minus G4 epsilon 4. So it's a very nice expression in the way that even though and it is the most general expression like this, that even though all the strain gauges are of different gauge factor, all the strain gauges are experiencing different strains also, but but if we know this, the G1 and epsilon, what would be the value of the unbalanced voltage? I can easily calculate and try to find out there. So here it is, if A is equal to 1, which is the most of the cases, so it would be E by 4 into G1 epsilon minus G2 epsilon, G1 epsilon 1 minus G2 epsilon 2 plus G3 epsilon 3 minus G4 epsilon. So using this one, we can get an idea, approximately, obviously because the strain is very small, the approximate is quite a standard one. It is not a very big approximation, so an objectionable approximation. We can find it out nicely using this formula. So we will discuss about this one, about the problems afterwards, but what is more important, we will take up some problems and etc. But what is more important is that we will take it up the next year, that is bridge balancing. We have already discussed that any instrument we want to make it, you should do some regular calibration, and at least 2 adjustments are required. That one is the zero adjustment and another is the full scale adjustment or the span adjustment. That means the zero, the output voltage should be zero totally, and also the output volt when no strain is applied, and when the strain is applied, or like this, there would be some finite exact values there which we require there. So this adjustment is very important. So for example, I just consider a simple bridge like this here. We'll take it up more details afterwards. So what we want is that if one of the strain gauge is the one of the strain gauge there. So what we require is that whenever the strain is not applied, the bridge should be perfectly balanced. But as I know that the gauge factor with epsilon equal to 0, the resistance of the gauge factor, say it is 120 ohm, but the practical value may be 19 ohm or 121 ohm, because this is I have already mentioned in the last date, there could be plus minus 1 ohm variation there. So naturally, even though I expect that all the resistance, other fixed resistance, are exactly 120 ohm like this there, but the strain gauge, because of the manufacturing defect and like this, there could be always a unbalanced voltage even with zero strain there. So naturally the U0 will not be 0 there, and so what we could do there, E0 is not equal to 0, what we could do to the balancing there? You could say that, okay, I will be making in this arrangement, I would be making this arrangement like this. I use a potentiometer, small potentiometer, and so that if there is a small potentiometer of this one of resistance, say maybe 1 or 2 ohm like this there, and I precisely adjust it so that till I get 0 whenever 0 voltage is being applied. So that is called the 0 adjustment. But the problem is that it has got a problem with it. What is the problem? Because maybe 1 ohm variation is there. Basically the variation is very small, 1 ohm or like this. And in fact, often we find that the with strain also, the E0 voltage is in order of microvolt or like this there. So naturally I will have to be, our instrument should be very delicate and like this. So whenever it is balanced, it should show very small voltage, maybe the less than a nanovolt or like there. But the point is that if we have a 1 ohm pot, say for example I make it a 1 ohm pot there, the problem is that the adjustment or this is much more difficult. It is much more difficult because for adjusting, which is so delicate that a slight movement will make the bridge unbalanced. So naturally, this is not a very good idea to use this one, because the variation of the potentiometer will be 1 ohm and 2 ohm, or the exact balancing would be much more difficult. So what we do is that in that way, I will just show the complete arrangement first, then we'll explain that one. And we know that the sensitivity has to be adjusted. So what we require is that one is the 0 adjustment. Number 2 is the sensitivity adjustment.
Sir?
Just 1 minute. And third one is the calibration. These three are important. Yes, please.
Sir, can you repeat like what is the problem with the potentiometer? Like,
now the point is that, say suppose we have a 1 kilo ohm potentiometer. Its size is large. You can vary it from this point to this point, 0 ohm to 999 ohm, or like this, or like this 1000 ohm. So you can vary it. So it is a large travel range, and we can make it like this. But the point is that if it is only 1 ohm, that means what will happen is that resistance wear will also be small. Resistance wear would be very small. And if we try to adjust it from this point to this point, hardly we will have a much role to play, and hardly we will be able to balance. Maybe from this point to this point, as I move, there would be a sudden jump. We will not be able to do it that way. My point is that on the other way, like this. Say, suppose I have a 120 ohm resistance. In parallel with it, if I put a, say, suppose a 10K resistance, you may calculate what is the R equivalent. R equivalent, you may calculate 120 ohm parallel with 10 kilo ohm. So maybe that is 199. I am just telling you, I have not calculated. Maybe 119.2. So the point, the adjustments of 10 kilo ohm is much more easier. So the point is that instead of connecting a potentiometer in series, an adjustment, it is much easier to connect a potentiometer in parallel and adjust it. Is it clear now? Maybe that because we have got a much from this point to this point, I mean, we can play it like this, and we can go the resolution. So because many of the things we may have 8-turn, 10-turn potentiometers or like this, we can do the things there. But if it is a 1 ohm potentiometer, its size is so small, the wear is so small, or like this, we will be able to hardly be able to manipulate. So what I wanted is that if we want to vary a resistance to a small value, or like this, for that one. So I am rubbing it up, but my concern is that these three things have to be done. That a zero adjustment, sensitivity adjustment, as well as the calibration. We will come to this one afterwards, but I will show you first of all the scheme there, then we will be able to explain this one. This sensitivity adjustment is often what we have it, the bridge, the supply voltage, BE, with the battery may go down. So naturally, for the same strain, it may give you a less unbalanced voltage. So what we want is that should be adjustable. So that way we can do a potentiometer, and that we will call it the sensitivity or span adjustment. This is obvious. Now, how to go for the zero adjustment? I suggest to make a larger resistance RZ1. This value is approximately 25 kilo ohm, and one is RZ2. Its value is approximately, say, 100 times R1. I will just show you what is R1 there. Mostly they are of unity ratio. So here it is R1, R1, okay, R1, R2, I just put it, R3, R4. Mostly they are of the same resistance nominally. So what we can say is that, suppose for the sake of simplicity, I say this is only one arm of the bridge, though we don't use a one arm of the bridge as the strain gauge. But for the sake of simplicity, I say this is our strain gauge there. So if it is the strain gauge here, which is not exactly 120 ohms, say suppose all of them are 120 ohm like this, but if it is not exactly 120 ohm, but maybe say 119 ohm there, what will happen? The bridge is unbalanced. So by which way we can make the bridge unbalanced? Bring it back to balance? I can adjust this port so that you can do whatever you can do, say suppose a start to delta conversion or like this. But the major thing is that let us forget this resistance also. I will tell you why this resistance also is required, but let us forget this resistance also. So the point is that at any position, the equivalent, this arm is equal to this R1 parallel to this part and R4 parallel to this part. So as a result, if there is a small unbalance in the bridge there, so one of the gauge here, which is not exactly 120 ohm, maybe 120 or 121 ohm, this one we can nicely adjust it. You can do the detailed analysis by converting into star, into a delta or like this, but I don't need it right now. So my point is that the same logic as I told, that any resistance parallel, if we put it any resistance high resistance parallel to it, we can very precisely connect and adjust the value of the resistance. Is it clear?
Yes, sir.
Now the question is that why RZ2? Why RZ2? What is the need of it? We have told that if you forget this RZ2, it would be simpler. You can see this is R1 plus the parallel this one and this one parallel this one. By adjusting this potentiometer, I can bring it back to 0 there. But there is always a risk involved. Suppose by mistake I connect it or to go to one or one end of this potentiometer like this there. So suppose this point I connect it by mistake at this end. So what will happen? The bridge will be directly connected. This RZ2 is not there. The whole voltage E will be coming across the gauge resistance R1. If I neglect the sensitivity or like this. So the bridge, it will be, so earlier two resistors were in series were across the voltage E, but now if I by mistake I connect it to the other end and bottom end like this there, the whole resistance, the gauge or the strain gauge will be connected across the total voltage of this one. And that may cause you, what is that? That may cause you some burning of this one. The current may go beyond its limit, and that's why to protect. So RZ2 is basically for protection. Protection of the gauge. So this is approximately so that it is 100 times R1, because even if you connect it, this bridge if by mistake I put it in one end, the bridge will not be, the gauge current will not be that much, and that will not be able to destroy like this. So this is the two things what we are saying. This one we can call it a zero adjustment, and this one I call it sensitivity adjustment, or sometimes we call it a span adjustment. So the span is that means the full scale reading. If we apply the full loading or the full strain applied to it, we know that the bridge should give this much voltage. If it is not, I adjust this potentiometer so that this much here. As I told, that two things we have to do it. One adjustment should be the zero adjustment, and adjustment should be the span or the full scale adjustment. One for the zero when no strain is applied, and when second is when the full strain is applied, and I need, say suppose it is a 1 volt should be the output, or 1 millivolt should be the output, so it should be exactly at 1 millivolt, otherwise we will adjust this part there. So I think there is another issue which is called the calibration. I don't have time. I mean, if you permit me, I can give you 5 minutes time. I can finish it off. So the calibration is another problem. Calibration is another problem because suppose this is a strain gauge, you mount it over, say, suppose a load cell, as I have told you, that where you have trucks, if you go to the roadways or highways or like this, you often find it out that way bridges on the side. In Hindi, they call it dharamkata. That means what is the loading of this truck, and like this, they often check it and find out. So that loading, this is done by using load cells, and the loading may be that is a few tons. The load cell may be a few tons or like this there. So the question is that if I want to manufacture a strain gauge instrument, load cell there at my laboratory, and the point is that, okay, I can, and all the things, this circuit and the subsequent amplifier and all the things we are doing it. But the question is that how would I test it? Whether it is giving you the calibration, that whether it is giving you the correct voltage output at the full load. In that case, I will have to, in my laboratory, I will have to bring a truck which is kept 10 ton weight or 1 ton weight like this, and put an identical wave bridge, which we do not have any possibility. We don't have the infrastructure to do that. So how to do the calibration for that one? For that one, what is done is a very simple thing, is that we put a switch and a few fixed resistance RC, and this is called the calibration switch. A fixed resistance, which is meant, RC means a calibrating resistance there. So the point is that whenever I push it, close it like this, this RC will be coming to this R2, parallel to R2 there, thereby altering the resistance of the R2 there, equivalent bridge arm there, and thereby generating some output voltage. And definitely, I can select, I can choose, I can design this value of RC such that the equivalent strain is generated. That means, say, suppose a strain of some corresponding to 1 ton is to be generated, and correspondingly I have calculated that much voltage will be the output. Instead of generating the strain directly, we put a calibrating resistance RC parallel to it with a switch, so that this RC, the moment I close it, this will come to parallel to RC, and that will cause you an unbalanced voltage of this one, which will be exactly the same as it was in the rated case. So if it is not giving you that unbalanced voltage, we will have to adjust the sensitivity. So these three are very important, is the zero adjustment, sensitivity adjustment, as well as the calibration. We will give you some problems afterwards and on this one. Is it okay? I'll stop here. Any other issue about today's lecture?
No, sir.
Okay. We'll discuss it afterwards, continue the other. So it's a very interesting thing of this one, zero adjustment, span adjustment, and calibration. So calibration is that actually we are not calibrating it, but without loading the system at all, because we don't have the infrastructure of it. So that is often done for many of the cases, many of the instruments. I have shown only for only one case here. Okay. Thank you very much. So we'll give you some more problems, and possibly on a Thursday we'll discuss also some of the problems. Okay. Thank you. Bye.